today I'll be talking about our experience doing embedded development with LLVM. Now, this is not the first time we're talking about this topic. Last year, my colleague Prabhu was actually here talking about our experience moving an existing product. In that case, it was the first generation of PixelBuds Pro over from the legacy GNU toolchain to our own in-house LLVM toolchain. Now, in that work, we've mostly focused on tools like the compiler using Clang and the linker using LLD. We didn't really do anything for runtime libraries, but we've made a lot of progress since then. And earlier this year, we've actually announced a second generation of PixelBuds Pro. These not only use Clang and LLD, they also use runtime libraries like the LLVM libc and compiler-t, libc++. In addition, we've also made a lot of progress on PixelWatch, where we use Clang toolchain for the ambient compute workloads running on some of the low-power islands. So in this talk, I would like to do a bit of a deep dive and talk about our experience using LLVM runtimes for embedded. So what has been our experience? Like, what we've noticed while looking around different products in this space being done at Google is that most projects use tool chains that are provided by their silicon vendors. Unfortunately, these tool chains are very often outdated. They're very rarely updated. And because silicon vendors use these tool chains to build platform libraries that come with their SDK, they can often inadvertently force these tool chains onto their customers. And all these tool chains come with their own C and C++ libraries. Every one of them might have a different API or ABI. And just aligning all of them can be pretty challenging. It gets even more tricky when you start mixing different architectures. We actually see more and more products combining cores with different ISAs, like ARM and RISC-V is pretty common. We also see developers doing development on different hosts, Linux, Mac, Windows. And so if you really need to come up with a set of tool chains that works across all of these, it can be a really daunting task. And what we've seen generally are two ways of dealing with this. One is just find a set of tool chains that work together and basically keep them the same for the whole lifetime of the product. But we believe there is a different way of doing this, and it's the one that we've been actually doing at Google for a long time for our production workloads and for projects like Chrome and Android, which is living it ahead, meaning you always try and compile everything from source, you always follow tip of tree, and you update regularly to avoid things like diamond dependencies and merge conflicts. And we believe that live ahead is actually a great model that could also work for embedded, and so that's what we're trying to do. We aim to provide an open source, cross-compiling Clang toolchain for baremetal, which doesn't have any legacy components. We use tools like Clang and LLD. We use libc, libc++, compiler-t as our runtime libraries, and we do all development directly in upstream. We don't carry any downstream patches. We closely follow tip of tree, which let us adopt new features as they keep coming into Clang, into all these libraries, basically immediately after they land. And it also let us provide a lot of feedback immediately back to the LLVM community. Now, one thing that is important about live ahead is automation and testing. You really want to know if something breaks in LLVM, like what broke, you want to be able to provide that feedback as soon as possible so the change can be reverted or addressed. Now, if you've ever done embedded development, you probably know that doing bare metal can be pretty challenging. There's lots of specialized hardware. It is really tricky. And that is especially challenging when you start dealing with LLVM. And so we believe to make this sustainable, we need a great platform. One that is publicly available, it is cheap, it has a great documentation. Ideally, it should be open source, which we can use as a proxy for all of the internal products that are not easily accessible by LLVM developers. And we believe that Raspberry Pi Pico might be a great fit here. This is a line of popular microcontroller products from Raspberry Pi. There are actually two generations. The first one, the Pico one, was announced in 2020. And just a couple of months ago, Pi Foundation actually announced a second generation, the Pico 2, which combines ARM and RISC-V cores. Now, one issue here is that Pico SDK, which is what you would use to build code running on these boards, does not support tip-of-tree Clang toolchain. At least it didn't until a couple of weeks ago. Earlier this year, we've actually partnered up with Raspberry Pi Foundation and the Pigweed team at Google, and we worked together to make Pico SDK the first baremetal project that we are aware of that can be built straight up with the open source Clang and LLVM toolchain using compiler RT, LLVM libc, and libc++. So how does it work? Well, we'll start off just by cloning Pico SDK straight from GitHub. Then we'll just use CMake. We'll configure the right compiler, the platform, and we'll point the build at a toolchain we want to use. Now you may ask, okay, where do I get a toolchain from? Well, if you've been at the LLVM dev meeting last year, I actually gave a tutorial on the LLVM build and CMake. And so I guess it's time to review how much you remember from that talk. So let's go on and build ourselves a toolchain. We're actually gonna write our own cache file. That's just a way to persist your settings and feed them into the CMake build in a more maintainable way. Now, I know this looks like just a lot of gibberish, but if you see through all the CMakeisms, the intent there hopefully should be fairly clear. What we're doing is we are selecting which targets we want to support. It's ARM RISC-V. We select which projects and which runtimes we want to build. Then we configure a couple of our defaults, so we don't always have to specify those on the command line. And we select which tools and which components we want to include in our toolchain. Next, we need to set targets for our compiler RT built-ins. This is going to be the two architectures supported by Pico 2. We set a couple of other options. Most importantly is the CMake, the C flags that are down at the bottom. And then we're going to do the same thing also for runtime libraries, that is libc and libc++. And that's basically it. At this point, we can fetch LLVM sources straight from GitHub. We can fire up CMake, point at our cache file, and build ourselves a toolchain that is usable with Pico SDK. And that's it. Now, if you don't want to go back and retype everything out on those slides, I've actually uploaded this file to GitHub, so you can check it out later if you want to and try it out for yourself. When it comes to individual runtimes, what has been our experience? For compiler RT, we've seen it to be mostly a great drop-in replacement for libgcc. We haven't really encountered any issues. On the corners, there are some differences, especially when it comes to more exotic types like float 16 or quantum 28. But in Pico SDK, we haven't really run into any of those. One limitations that we're aware of is that LLVM right now is not aware of the compiler runtime that is being used and cannot really take advantage of routines that are specific to compiler RT. But this is more of a missed optimization, but still is something that would be nice to address in the future. On the libc side has been in development for the last couple of years, and we believe that it is finally becoming ready for broader adoption, especially in the baremetal world. It is a great permissive license C-library implementation. It can be scaled from warehouse to a tiny board like a Pico. Now, to make it usable for Pico SDK, we had to implement a bunch of missing functionality like higher math functions, malloc implementation, basic I/O support. There are still some parts of libc that are missing, like startup code, semi-hosting I/O, or threading. All of these are aspects that we're actively looking into, and we hope to implement over the coming months. In addition, we've also started working on the low-level embedding API. The way to think about it is it's a little bit like POSIX or a system call layer, but for embedded. Basically, it's a set of symbols that LLVM libc expects any platform to provide, because we don't want to hardcode knowledge of all these individual platforms like Pico SDK or FreeRTOS and other RTOSes into libc. Instead, we want this to live on the platform side. Right now, we only have a handful of functions to do things like standard input, standard output, termination, but we expect this interface to grow over time, especially as we add things like threading support. On the libc++ side, libc++ already has a lot of options that let you disable unnecessary functionality, and we use those, but we've also found out that we probably need more configuration points to better support embedded environments, because there are still places where libc++ uses functionality like dynamic memory allocation, TLS, or float, and this may be undesirable on many baremetal platforms. We also had to introduce support for building libc++ with libc, which wasn't there before. So if I go back to my original example, in addition to what I already had, we also need to set a couple more options to disable the functionality that right now is unsupported or undesirable. Most notably, there are things like localization, Unicode, Y character support. Now, this is temporary, like this is something that's being actively worked on in libc, and we hope that over time, all of this will get implemented, so many of these won't be needed in the future. All in all, I think becoming toolchain, building a toolchain is becoming easier. Now, up until recently, it wasn't actually possible to build a fully functioning bare metal toolchain within LLVM project.git at all. But with that being said, there's still a lot of room for improvement. Like what you see before in that CMake cache file, there's still a lot of boilerplate that I think we can probably reduce and eliminate over time. But things are, pretty okay. Runtime's build already has basic multilib support. Multilib is really important on bare metal because of the great variability of hardware. But the existing multilib support is fairly limited. It is really inefficient. It requires a lot of CMake invocations that really extend build times. There is also no support for the new YAML-based configuration format. But beyond that, I'm actually not even sure if in the long term we should be using multilibs. I think we really should explore the idea of actually building runtimes on demand from source using the right flags. It's something that we've been experimenting with internally in our Pigweed project, and we do have a minimal working prototype, but right now it's very build system specific, and over time we would like to see if this is something that we can generalize and support directly in Clang and LLVM. What we've also seen is that performance still has some gaps. A lot of bare metal projects are sensitive to binary size and memory usage. Making them fit is often exercise in cargo coding. What we've seen is GCC generally tends to better balance size and performance at the OS level. With Clang OZ, we would often get smaller binaries, but that can actually come at the cost of worse performance, which is not always desirable. We can maybe recover some of that in the future with other tools like ML inliner, but I think there is more we can do. Also, what we found out is stack allocation in LLVM has a lot of gaps, which can result in inefficient stack usage, and this is also frequently causing problems on bare metal. There is a lot we can do actually for tracking book on the slide, which has a lot more details. Here's just an example from one of our projects, like all the flags that we would set just to make everything fit under our budget. And while this works, it is not very maintainable. Like we really don't want to be copying these flags from project to project. I hope that over time we can come up with something that's better than this. Debugging can be also challenging. One of the things that we've noticed is that right now LLVM and LLDB doesn't support all of the dwarf CFI constructs. This can be a problem, especially when you are dealing with handwritten assembly in places like interrupt handlers, if you want to support unwinding, which we actually occasionally run into when doing embedded development. LLDB support for remote also has some gaps. For example, the RISC-V32 support is currently mostly absent. It's something that we would like to improve. But assuming that all of these issues get addressed, and I believe they will over the coming months, I think that LLVM is a great fit for embedded. And I believe there's a lot of things in LLVM that embedded developers could benefit from. But I think LLVM developers also need to be aware of constraints that these systems have. So let's take a look at some of those. First one is support for heterogeneous memory. This is super common on embedded. Embedded systems use tools like attributes and linker scripts to place symbols on specific memory regions at specific addresses. But right now, these are not compatible with LTO and PGO. LTO is a fantastic tool. We've been doing some early experiments in embedded space. We've seen binary size reduction of more than 20%. But LTO today is not compatible with linker scripts, and there's a problem because these are really common in bare metal. Similarly, PGO can provide great performance improvements, often more than 20%, but it doesn't really take into account aspects like memory placement, which again is a requirement. We would also like to take a look at post-link optimization tools like Propeller or Bolt in the future. That's still an open area of research. Next, sanitizers. Sanitizers are just fantastic tools for finding bugs, but using them on embedded systems is really challenging due to the memory constraints. We actually used successfully UBSAN in some of our development for finding things like misaligned accesses, But what we also notice is that while UBSend has several runtime implementations that are tailored to different environments, none of them is the right fit for bare metal, and we'll probably need another one. ASEN doesn't really work right now, mostly because the instrumentation is just too high, and we really need to find a way to reduce it to make it suitable. There are other sanitizers right now. I'm not really sure if those are ever going to be feasible on embedded simply due to high overhead, but it's something that we are still looking into. And sort of more general theme is that all of the sanitizer runtimes were originally developed for POSIX and later ported to platforms like Windows. And they often make assumptions about the underlying platform kind of looking like POSIX, but that's not really the case on embedded, and that makes porting really difficult. And I think there is more work needed, not just cleaning up the implementation to make them more portable. And finally, source code coverage. This is a very useful tool that can help track how you're doing on testing. But what we know from experience is that the existing profile runtime has a lot of issues, code quality issues that complicate porting, and more work is needed there. There are opportunities for also reducing instrumentation overhead of core coverage. Features like single byte counters, conditional counter updates, or such encounters. All of these are things that we're actually working on. There is active community of developers trying to improve source code coverage and make it more usable on bare metal. So to summarize, I think that LLVM is a great fit for embedded. LLVM is a cross-compiler, which means that a single tool chain can be used for all the different targets, all the different hosts. You don't need multiple tool chains, which simplifies maintenance. And we're trying to make it easier to build a complete tool chain within a single LLVM build. LLVM now offers modular, permissive license C and C++ library implementations, and we're trying to make those really usable on bare metal. We're also actively thinking about continuous testing. Our long-term goal is to have a bot in LLVM CI that will actually be using Raspberry Pi Pico and doing continuous testing to make sure that we don't regress, for example, support for bare metal in libraries like libc and libc++. And then finally, there's a lot of great tools and features that could really help embedded developers, tools like profiling and LTO and sanitizer and coverage. And we really want to bring all of those to bare metal. If any of these aspects are of interest to you, please do get involved. There's multiple ways of doing that. We have an active and growing community, which meets every 4 weeks. It's on Thursdays, 9 a.m. Pacific times over Zoom. Everybody's welcome to join. We also have Embedded Toolchains workshop. We actually had a second instance of the workshop just yesterday, and hopefully it wasn't the last one. Hopefully we'll have another one next year. And then finally, we also have an embedded label in GitHub that we use to track issues that are related to embedded usages. So if you want to see what issues we're working on, please use that. And with all that, I would like to thank you for your attention, and I'm ready to take your questions.
Thank you, Petr. Questions, please.
Yeah, so I was just curious if I have like an x86 machine and I want to build a tool chain for like both RISC and ARM, is it possible for me to build not just the compiler but all the runtimes and everything like just using like a standard CMake configuration, or do I have to do like multiple steps?
No, yeah, it's possible. That's exactly what we do. Like at Google, we have a tool chain that currently like in a single build builds runtimes for Linux, Mac, Windows, ARM32, RISC-V 32. Like it's probably, I probably lost track, it's like 16 platforms in total. So it's definitely possible. Now, it is with a single top-level CMake invocation. Internally under the hood, like the CMake would spin up sub-builds to build those individual, like runtime libraries for those individual targets. So there is a little bit of overhead, and this is something that we're actively working on, but it definitely works. And it is like being actively used and tested.
Hey, Peter, have you thought about like the Rust embedded use cases? We hear the keynote speaker like also mentioned about the fact that they had to like use the GCC for some of these targets? Like, what are your thoughts on that space?
Well, that's an interesting question. I haven't really actually looked at the embedded support in Rust, so I don't know if I can give you like a great answer. Basically, everything that already works in LLVM should like work for Rust. So we already have support for ARM and RISC-V, which are like the most common architectures used in embedded. But as far as like other aspects like runtime libraries, which our experience are like some of the trickiest parts, I don't really have a great answer. I think one thing that we definitely need to look into is using LLVM libc in Rust or supporting that on the Rust side, which hopefully we'll get to like soon. But I would imagine there's probably more.
Thanks for the talk. You mentioned that none of the UBSAN like runtimes fit your use case. I was wondering if like the trapping UBSAN like build mode like was suitable for bare metal, because in that case like there's no runtime at all. It's just like you just emit a trap instruction when things go bad.
So yeah, great question. So it really depends on what is your use case. Like in our experience, the trap runtime is great like for like production. Like when it traps, like something is wrong. But during development, you typically want like more feedback. You want to know like exactly what went wrong. You ideally want like some pointers like which part of the source code this happened in, and you only really get those with the full runtime. And so like from our perspective, what we would really like is something that combines the overhead of the trapping runtime, which is really like the most we can fit on a bare metal device, with the full diagnostics that you get from the full runtime. And we actually think that this is possible. Like one area that we are looking into is reusing the verbose trap that has been like recently introduced into LLVM. So we can actually do it with the assistance from the debugger. So in the code, you would only have a trap, but you would then use Dwarf and in combination with something like an LLDB to then like from that trap and from the Dwarf information to reconstruct the full diagnostics, which we think might be a good fit for these devices.
Cool. I had a second question as well, because you mentioned that you like to live on top of head. I think that makes a lot of sense for like continuously testing. But I was wondering if you actually shipped like using like head, because that seems like it might be quite risky.
No, we do, yeah.
Okay, well, I'm glad that works.
I mean, yes. I mean, there are always pros and cons. Like, but we've been we've been doing this not just for embedded. We've been doing this for like internal Google production. We've been doing this for projects like Chrome, Android, Fuchsia, and I don't think there's any reason why it shouldn't work for embedded. And if there are any reasons, like be not such a great testing, that's something we should improve.
Cool, makes a lot of sense. Thanks.
Thanks, Peter, for the talk. Is there any plan for adding support for debugging tools for embedded, when you build embedded images to compare and then build tools versus other tool chains?
Can you be more specific, like what kind of tools? Like are you thinking anything like beyond, say, like LLDB or just like binary LLVM
like
tools?
for example, image layout issues or
yeah, that's something that like we continuously keep thinking about, because like we have people coming to us and asking us for better tools. Like we see a lot of developers have been like using tools like Bloaty and Bloatface, but those have issues. Like they work in some cases, they don't often work in other cases. I know this is like something that people keep asking about, and we've been thinking about it. Right now, it's mostly just an issue of like not having enough resources to build something better.
Got it. Second question is, if I may ask.
Yeah.
So on the instead of devices, can we use QEMU for testing?
Yes, but at least in our experience, like the support for like these like bare metal platforms in QEMU is fairly limited. So we did not really have a great experience doing that, but that might change and improve over time as QEMU improves.
Hi. About the limitations you mentioned, do they affect all the targets equally? More specifically, is RV32 worse than ARM32 in any way? Or Is anything missing for RV32 that is supported for?
Yeah,
RV32?
there are like some aspects in RV32 that, in our experience, like there are more gaps. But I think this is mostly just the consequence of the backend being younger. So, for example, like machine outliner, like in the ARM like ARM backend machine outliner, there is a lot of heuristics for like dealing with lots of like complex constructs. The one in the RISC-V backend is really like super basic. It doesn't really do much. This is something we're tracking. Hopefully this will get improved over time. There's probably more places like that.
Thank you, Petr. We will start our next talk in 5 minutes.